Hi guys, my name is Emily and today I'm going to run through for you rate of chemical reactions. So where does this fall under your study? So rate of chemical reactions is for the chemistry unit under unit 3 and it's area study 2. So what is the intention of this video? Hopefully by the end of the video you'll be able to explain chemical reactions in terms of the collision theory. You'll be able to tell the difference between an exothermic and an endothermic reaction, determine the factors that affect the rate of reaction, and understand the role of catalysts in chemical reactions. So basically, at the end, you'll be a pro at chemical reactions. So why are chemical reactions important? Chemical reactions are happening all the time, every day in everyday life. Here is an example. So most of you probably have seen this picture before, and it is the process of photosynthesis. What some of you may not have seen is the chemical reaction that comes with it. So here we have, what happens is that you have carbon dioxide and water. When that's exposed to UV light or sunlight, that will produce glucose, which is energy, and oxygen, which is what we need to breathe. Another thing you guys may know is beer. So beer, it's alcohol, as many of you would, I assume, know. And what happens is it's actually the fermentation of glucose with yeast. So basically, you have glucose goes to ethanol and carbon dioxide. So we have chemical reactions happening all the time, and it's good to know why and how they're happening. So first point I want to touch on is the collision theory. So for you to have a successful chemical reaction, your reaction particles need to collide together to produce a product particle. So you need two things for a successful chemical reaction. You need sufficient kinetic energy to break the bonds of your reactant molecules, so then they can then form to product molecules, and you also need the correct orientation. So let's go through some examples. Let's assume all the following examples have enough kinetic energy to be able to break the bonds, but I'll show you how orientation can be quite important. So for our first example, so this is collision 1. So we're going to assume that these black particles are carbon, these white ones are hydrogen, and this is a chloride, so a negatively charged ion. Here we have a double bond, so that makes this ethene. We have hydrogen, which is positively charged, going towards a negatively charged double bond. So that's going to happen. That positive charge and that negative charge will want to be with each other. However, when we swap that around and we have our negatively charged chloride going towards a negatively charged double bond, that's not going to want to happen. Same here. This is just completely not going to happen. They're coming in at the wrong way. And here, this is just coming in from a diagonal point. These are going to repulse against each other because they're both positively charged. So something you guys may have already seen is called the Maxwell-Boltzmann curve, which explains how chemical reactions can occur. So here on our y-axis, we have our number of particles, and on our x-axis, we can think of this as the kinetic or collision energy. The area under the graph is the total number of molecules. I'm already going to warn you for my awful highlighting skills, but let's see how we go. This line here is basically the point where we have the most amount of particles colliding. So the energy of the greatest number of particles. Then this line here, we're going to have this as our activation energy. And I hope you all know what that is by now. So basically anything past this point is where particles have enough energy to react. So we don't actually have a lot under this curve where we have enough for the particles to react. Anything here is where the particles have less than the average kinetic energy. And here they have greater than the average kinetic energy. You see, even though they still have greater than the average, unless you're past this point, you're not going to have enough energy to react. Okay, so now let's talk about exothermic and endothermic reactions. So an exothermic reaction releases heat, and that's when you're going to have a negative delta H. An example of this is when we burn coal. You'll be able to tell because most of your reactions should be given to you with a negative delta, with a negative or a positive here. And from this reaction, so basically if you touch something like a beaker or a conical flask where an exothermic reaction is happening, you're going to feel it turn hot. Opposite is then endothermic reaction, which absorbs heat and will have a positive delta H. For example, when we melt ice cubes, as you can see here, if you touch that, it'll get cold. However, this reaction here, beware of that. It's not a chemical reaction, it's actually a physical reaction because we are having a solid state of water go to a liquid state of water. So be careful of that. here are the graphs that clearly show this. These are very nicely drawn, and I admit I did not draw them myself. But basically, you can see why we'll have a negative delta H here, as we're starting here, and then we go down with our products. So we're going to have a negative change in our delta H. Whereas the opposite happens here when we have our endothermic reaction, we go up in energy. Okay, so now I'm going to talk about the factors that affect the rate of reaction. So we have temperature, we have surface area concentration, we have gas pressure, and we have the presence of a catalyst. So for temperature, when you increase the temperature, this will increase your average kinetic energy and therefore increase your frequency. So as you can see here, this green line is our higher temperature. So if we say our activation energy is here, which I actually already drew, that means we're going to have a higher area under that graph that has a chance of a collision occurring than if we have a lower temperature. For concentration, when you increase the concentration of your reactants, that means you increase the number of collisions as there are more particles. We have more particles here. That means that more have a chance to hit each other, which increases our chance of a successful collision. For your gas pressure, if you increase it, so we go from here, we've increased it. We are making these particles closer together. That will increase your chance of a collision occurring, therefore increasing your rate of reaction. And when you add a catalyst, so this will decrease your activation energy. So we've now gone from here to here, which would increase the amount of particles under that curve that has a chance to react. Therefore, it's a more successful collision. So let's also discuss the role of a catalyst. So basically, a catalyst increases your rate of reaction by decreasing the activation energy and provides an alternative pathway. This sentence is basically the sentence I used throughout my entire year 12 for chemistry, and it always got me my marks. So that was something my teacher showed us. And as you can see here, so we're going from not having a catalyst, and when we have those alternative pathways, we have decreased the energy that is now required for a reaction to occur, hence obviously increasing our rate of reaction. Okay, so final tip. If you put in your hard work at the beginning and you learn the concepts, it will really pay off, because that means you'll be able to apply that knowledge to any question given to you. Don't try and learn how to do the questions. Learn how to apply, how to figure out what the knowledge actually is. And just another thing is stay safe. Make sure you have time for yourself during this year. Still be healthy. I know we all want to sit on the couch and eat a bag of chips every day, but we still need to maintain our health. Good luck this year. I hope you guys nail your exams.